Okay, so in today's lecture, we're going to be covering the exponential function. Well, to be more specific, the natural exponential function. Now, recall from the previous lecture or section that increasing functions are one-to-one, which means that they have an inverse. So the natural logarithmic function, ln of x, is increasing, which means it has an inverse. And we're defining its inverse function as e to the power x. And this function here is called the natural exponential function. So ln x is the natural logarithmic function, and e to the power x is the natural exponential function. Now, by definition of being inverses of each other, we have this very important property here that y equals e to the power x if and only if x is equal to natural log of y. Okay, so this is basically a restatement of these this being an inverse of each other, these being inverses of each other, together with the properties of natural logarithms. Okay, so this should be familiar from a college algebra course or a pre-calc course, but I thought that maybe I should just maybe give examples of how to use this to solve equations, just in case you need a refresher. This would maybe be like review. So maybe say they solve, I don't know, 7 equals e x plus 1. Okay, solve this equation for x. This is kind of a standard college algebra question, or so how would you do this? Well, you would say, okay, you have this equation with an exponential e on the right-hand side. So one way to eliminate that exponential e is to take the natural logarithm on both sides of this equation. So maybe solution. So that's what I'm going to do. This means that I can take the natural log on both sides. Now, by the exponent property of natural logarithms, we have that this is equal to natural log of 7 times x plus 1 times the natural log of e. Okay. All right, so, but natural log of e is just 1, right? So then we get natural log 7 is equal to x plus 1 times 1. So in the end, we get that x is equal to natural log of 7 minus 1 if you solve for x. And that's again because natural log of e is 1. Okay, so these types of problems you should probably review. Maybe I'll post like a short review, like a document on Blackboard, or put a link to another YouTube video going over these types of problems. But this is really college algebra, pre-calc type of things. This is a calculus course though, so we need to look at differentiation and integration, and in particular, we need to look at differentiating this natural exponential function, which we can do with the following theorem. Okay. So let u be a differentiable function of x. Yeah. Function of x. Okay. So then one here, d dx, so the derivative with respect to e to the power x, that's just equal to e to the power x. Part 2, the derivative with respect to x of e to the power u. Well, u is a function of x, and we're taking the derivative with respect to x. So this is going to be the derivative of the outside, which is e to the power u, times the derivative of the inside, du dx. Okay, so maybe how could we derive that? Because I'd like to get at least like one argument. I know this isn't a standard calculus course and we don't prove everything, but I kind of think we should maybe prove that. How would that look to prove this part 1? Well, we do know about derivatives of logarithms, right? The natural logarithm, and we also know about rules for exponents. So maybe let's just, I hope I don't mess this up. So let's just say, let's look at the derivative of natural log of e to the power x. Okay. Now, does this help us at all? Well, this is like saying, does this help us? Well, this is like, yeah, I can use this rule for exponents and bring the x down. Yeah, right. So, yeah, I can do that. So this is like saying d dx of x times the natural log of e, and that's just a 1. So it's like d dx of x, right? Natural log of e is just 1. So the derivative of that is equal to the derivative of that, which is equal to just 1. Okay. Oh, I see it now. Okay, so we know how to take the derivatives of natural logarithms, right? So like this right here, that's like u, right? Natural log of u, right? So what do we know? I'm kind of going on a tangent right here, but we know that d dx of natural log of u, right, is equal to 1 over u times du dx, right? We use that quite a bit. So this is like d dx of ln of u, right? And we know that's equal to 1. So this side is equal to, all right, so what is u? U is equal e to the power x, right? So d dx of ln of u, this side is going to be equal to 1 over u times the derivative of this guy. This is equal to 1. That's it. So then the derivative of that is equal to u times 1. But what is u? E to the power x, right? Hopefully you see that. So then d dx of e to the x is equal to u times 1. So all of this implies that d dx of e to the x is equal to u times 1, but u is that. That's not a formal proof, but it's an argument for that. It's messy. I kind of did it for a moment, but that's how you would argue that that is true. And I think that it's important for all of you to at least like see sometimes that if you want to validate something, you do have tools to use that. You can just use the definitions you know and try to derive out why that equation is true. Okay, but we've proven that one, we can take that one to be true. We're going to use those quite a bit. So let's look at actual examples of using this theorem. So examples, so A, let's say maybe find dx and the derivative with respect to x of e to the power 2x minus 1. And then maybe example B, let's look at the derivative with respect to x of e to the power negative 3 over x. And yeah, let's I think I can fit it here. Let's look at C, and that will say find the relative extrema of f of x equals to x to the power times e to the power x. I'm sure you can read that. Okay, so I'm gonna go ahead and pause the video and let you work this out, and then we'll write out the solutions in about 5 minutes. Okay, so let's go ahead and look at the solutions to these problems. I went ahead and rewrote them on my board so that I have more room to solve them, because I think these might take a little bit more. But let's go ahead and start with example A. So find the derivative with respect to x of this function here. Well, here u is going to be 2x minus 1 in the statement of this theorem. So this is going to be very simple. It'll be e to the power 2x minus 1 times the derivative of u, which is just going to be 2. So that's it. It's just 2e 2x minus 1. So that's pretty straightforward there. You just have to treat that as your function of x. Okay, so here, actually, I could probably fit this one right here. I have a feeling that one might take a little while. So, B, we want the derivative with respect to x of e to the power negative 3 over x. Now, this is equivalent to saying we want to find the derivative with respect to x of e to the power negative 3 x to the minus 1, right? So then this is just going to be e to negative 3x to the power minus 1 times the derivative with respect to x of the exponent. So it's going to be negative 1 times negative 3, positive 3, and then x to the power minus 2. So altogether, we're going to have 3e to the minus 3 over x all over x squared. If you simplify everything out. Okay. Now, we need to find the relative extreme of some exponential function. C. Find the relative relative extrema of f of x equals to x e to the power x. Okay. All right, so here in the whole solution process, in particular, we need to find the critical numbers. And let's see. All right, so f prime of x. So it looks like we have a product of functions. So it's a derivative of this times that plus that times the derivative of that. So derivative of x is just 1. So 1 times e to the x plus x times the derivative of e to the x. But the derivative of e to the x is just e to the x. So now, this derivative exists everywhere, so the only critical numbers are going to be the numbers where the derivative is equal to 0. So let's set this equal to 0. Okay, and then we can factor out an e to the x. Like that. And there's only one possible solution, right? X equals -1. This is always positive. And the only time this would be 0 is when x is equal to -1. So that would be a critical number, but not the solution to the answer. We need the relative extrema. So then f at -1 is going to be -1 over e. So the relative extrema is going to be -1 comma -1 over e. Okay. So those are the solutions to those example problems. Okay. So now we're going to move to logarithmic, not logarithmic, we're going to move to integrals of these natural exponential functions. So let me pause the video real fast, clean up my boards, and then we'll get started. Okay, so as we just learned, the derivative of the exponential function is, well, exponential e to the power x, the derivative of that is e to the power x. So when looking at antiderivatives for the indefinite integral, this is immediate, according to the theorem that we gave about the derivative of e to the power x. The same thing holds for e to the power u, where u is a differentiable function of x. These are immediate consequences of that theorem I wrote down about the derivatives of these natural exponential functions. So, provided you are comfortable with the techniques of integration that we have developed, these types of problems here should not be too difficult. For example, here we have e to the power u, right? So we're in this scenario here. We just need to find out what u is. We're using a change of variables. So if u is equal to 3x plus 1, then du is equal to 3dx. And I don't see any 3dx up there. So if I divide by 3, I get 1/3 of du is equal to dx. So then this integral here becomes, well, I replace this by u, and then dx by 1/3 of du. But since 1/3 is just some constant, I can bring that outside the integral. And then I have that this is 1/3 of e to the power u plus some constant c. So e to the power 3x plus 1 plus some constant c. Okay. So this, again, provided you are comfortable with integration, change of variables, you should be okay with this stuff. So let's look at this one here. We have the indefinite integral of 5x e to the power negative x squared dx. So let's see if we can use change of variables to write this as a simple integral in terms of the function u, which is a function of x. So if u is equal to negative x squared, I suppose, I'm just guessing right now. I'm not guessing. I know that this is like this is my u, right? I just don't know if it's going to be negative u or just u, but I'll just assume that it's u. So then u is equal to negative 2x dx. So now I see e to the power u, but then I see 5x dx, which is not the same thing as negative 2x dx. So can I get a 5x dx in there somehow? Well, if I divide both sides by negative 2, I get negative a half du is equal to x dx. But I really want 5x dx, or I could take the 5 out, it doesn't matter. If I multiply both sides by 5, I get negative 5 halves du is equal to 5x dx. So now I can replace everything in this indefinite integral in terms of u. That times that is equal to that. E to that is equal to e to u. So I'm going to go ahead and do that now. I'm going to take out the constant negative 5 halves. And on the inside, I just have e to the u, u. And we know how to integrate that, right? So this will be e to the u, which is negative x squared. And then I have my constant. There it is. Okay. Seems simple enough. So before we end today's lecture, let's do a definite integral. And the definite integral works the exact same way. We just define the antiderivative, evaluate the limits of the definite integral in terms of x or u respectively, and then that's it. Okay. So let's look at an example. Suppose we have the definite integral from 0 to 1 of e to the power x over 1 plus e to the power x dx. Let's code my new chalk. Okay, so I suspect I can already see that if I let u be 1 plus e to the power x, then du is going to be e to the x dx. So this is actually really simple. I probably should have picked a harder one. We let u equal to 1 plus e to the power x, then du is equal to e to the power x dx, right? So then so that times that is just du over u. But we do have to change our limits of integration now. So this is in terms of x, we need it in terms of u. So when x is equal to 0, u is equal to 2. Right? 1 plus e to the power 0 is 2. And then when x is equal to 1, we have u is equal to 1 plus e. And then we have 1 over u du. And we know that antiderivative, right? We know this integral. This is natural log absolute value of u. So this is going to be natural log absolute value of u evaluated from 2 to 1 plus e. So this is natural log absolute value of 1 plus e minus natural log absolute value 2. Whatever that number is. Okay. So these problems are pretty important. So I have some homework problems for you to do. But I think that would be the end of today's video lecture. So I'm going to go ahead and stop the recording now. Or so my students can see it, I'll write it out first. 5.4 homework. 3 through 13, 33 through 47, and 97 through 115. And this is going to be due next Monday. And now I'll stop the recording.